in data science. So this is the just collection of notes. Yeah, and the weird thing is I don't need to study at this point. Like, exam is done, so there's literally no reason for me to be doing this. But well, we're gonna do what we're gonna do. So so these are like the last year notes which people compiled. So there was a scribing practice in this course, and they don't have it now. Like now they just put like lecture notes as proper, like it's like a book almost. That's how the lecture notes are. Not these, but the ones which I made these from. Alright, so these are just like some very basic sort of data science concepts, not all that complicated. We'll just go through them one by one. So Markov's inequality, this is from statistics. So the probability that so x is, suppose it's a non-negative random variable, then the probability that x is bigger than a or equal to a is less than or equal to expectation value of x upon e. And this is pretty easy to see, because basically expectation value of x is like an integration or a summation of the probability that x is a particular value, let's say x equal to b, that times of b. So you can split that into two parts, one where x is less than a and one where it's bigger than a. So the less than a part is some positive or non-negative quantity, so you can say it's bigger than or equal to 0, and then the bigger than a part, that is going to have some density, right? But all of the values that x will take will be bigger than a, so you can straight up say it's going to be a, so it's bigger than or equal to a probability that x is bigger than or equal to a, right? Because it's basically all the values which are bigger than a, so that's essentially the probability that x is bigger than or equal to a. So it's pretty easy to prove, and let's not waste time on this thing. And so yeah, this is one of the most basic inequalities. Chebyshev inequality is slightly different, but this can also be proved easily using Markov's inequality, where you take this thing, the mod of x minus mu, as the new random variable, because then now it's a non-negative sort of thing. But you can also prove this pretty easily using variance. And yeah, so this, okay, for using Markov's inequality, you don't need x minus mu mod, you need x minus mu squared, because when that happens, the expected value is called the variance, right? And so you can easily get this. So basically the variance is just the expectation of x minus mu squared, which just happens to be another variable, right? So that being, you know, less than or equal to some particular value, that's that probability, sorry, bigger than or equal to some particular value, that probability is yeah, should be possible to say it's going to be less than or equal to equal to the expected value upon the value itself. So in this case, the expected value is sigma square, the value itself would be a square, because this translates to x minus mu squared bigger than a square, right? And so just using Markov's inequality, you can easily prove it, or you can do it the organic way by writing the variance and then doing the usual stuff that we did for Markov's inequality. Moment generating function, that's where it gets weird. So just to read through it, because this is going to be some dense math. So basically it's the expectation value of e power tx, where t is some variable, some parameter which we haven't set yet. But when you do this expectation, so x is once again our random variable, when you do this, the function is a function of t, basically what you get is called the moment generating function, right? So you put in the values of t and you get different values out. And this is extremely useful, because using this you can generate all the moments, and that's why it's called the moment generating function. Essentially the nth moment, which is the expectation of x power n, that's the nth derivative of this function evaluated at t equal to 0, and it's easy to see why that's going to happen. Also, you do this basically using e power tx equal to this Taylor series expansion and then putting the expectation inside, which you can do, by the way. And so you get this thing, and this is like related to characteristic function, Fourier transforms, and a lot of other things. And so this is pretty cool. In fact, it's basically a Laplace transform, which means that when you have convolutions, you can get the moment generating functions using the convolution theorem, and that's pretty sweet, I would say, right? There's also the cumulative generating function, which you should read about, I think, but that's a bit more complicated, so we'll leave it. Like, we won't do that right now. Right, Chernoff bound. So basically the general Chernoff bound is like this actually. So suppose x is some random variable and y is e power tx, right? So you can have, so y is like non-negative, or in fact it's positive, right, if x is going to be a real variable. So then you can use Markov's inequality and say a bunch of stuff, basically this stuff, and using these two, what you're allowed to say is like it's that x bigger than or equal to a is bounded by this thing. So it's the minimum of the moment genetic function times e power negative ta, where t is a positive number. And similarly, if t would be a negative number and you want to minimize this, that would be x less than or equal to a. So that's the Chernoff bound for a general random variable. Now we are interested in the Chernoff bound for a Bernoulli variable repeated multiple times, which basically is a binomial distribution, right? So suppose xi is a Bernoulli, then for the binomial distribution s equal to summation of xi, right? You can write stuff like this. Basically the mean, you also know the variance and all that, and then you can use the Markov's inequality for e power ts. But remember, this e power ts, so this condition is basically the same thing as saying that ts is bigger than a, right? Now to get the expectation of e power ts, you can use the very basic fact that all of these are independent and randomly distributed independent variables, and they are also identical. So it's IID random variables. I'm just eating something. Okay, so using Markov's inequality, you get all of that. And then from there, it's a bunch of approximations until you get something like this. So this is the final inequality that you are going to aim for. So this is the upper tail bound, right? So basically the probability that your variable is deviating from the mean by some fraction, some positive fraction, that's bounded by this number, which is once again bounded by e power negative mu d square upon 2 plus t. So if you write all, and similarly you can have a lower bound as well by doing the same sort of stuff, in fact. Yeah, but so compiling all of this, you can write these things. So the probability that x is bigger than or equal to 1 plus delta mu, that's going to be less than or equal to this exponential, and if it's 1 minus delta u, it's this exponential, right? And then you can combine them by writing this. So it's 2 e power negative delta square mu by 3, right? So basically you just add these two and you figure out that okay, this thing is already less than or equal to e power negative delta mu square by 3, and so you can do this thing. And yeah, I mean that's only going to be true if this delta square mu upon 2 plus delta is actually a bigger value than delta square mu by 3, and that only happens if delta is like 1. I mean, it's less than 1, but I mean, you can assume that happens, right? So as long as delta is less than 1, this holds perfectly true. And usually it is. How did this thing? Let's go to some actual algorithms. First, you just have like unsupervised learning. So you just detect patterns in images, outliers, etc. So this is all this is about. You're not going to be doing any supervised machine learning right now. It's all clustering and like unsupervised classification and things like that. So it's going to be k-means. There's going to be Gaussian mixture models, and that's pretty much it. And then there's some dealing with data sort of stuff like big data, but that will come later. Right now it's just clustering. So the distance function could be any of these things. It could be an LP norm, and just to remind you, L0 and L infinity norms are kind of special. So for example, the L infinity norm, it just takes the maximum value out of maximum magnitude value out of all the elements in your vector. L0 norm just finds how many vectors and how many of these values are non-zero, and that's what it gives you, right? So basically it's a count, and this is the max, right? LP norm you can define pretty easily. So just as you have L2 norm, L1 norm, you have LP norm. So norms give us an easy way to define distance, because you can induce a notion for distance using this thing, right? So basically you can say that okay, the d of xy is going to be the norm between x minus y, so norm of x minus y. And yeah, so you have an easy distance measure. But sometimes this isn't the kind of distance that you are looking for. You can also have something like this. So here the distance of xy is 1 minus the angle between them. This angle thing is called the cosine similarity, and it's going to as like x inner product y upon the norm of x, norm of y. So if you're like dealing with an inner product space where the norm is defined using the inner product, this is perfectly fine. You can use this straight up. We can also have these kind of distances. So for a set, the Jacquard similarity is given by the intersection upon the union. All right. So like if A and B have exactly the same sets, then there would be, you know, the intersection is equal to the union. So we just have that as a similarity. While the distance is so this is how do I say this? Okay, never mind. Let's not say this in fact. But yeah, so this is how the distance is defined, and the distance is just 1 minus Jacquard similarity. And yeah, so edit distance for strings. So yeah, so between strings, if you want to have a distance, one easy way to do this is using edit distance, and this is what like I don't know, genome algorithms use. So like BLAST and all these guys, they use the edit distance and some other stuff mixed with it to figure out like a probability of one string evolving to some other string, something like that. And then there's this KL divergence thing. So basically you'll have to think about cross entropy first. So cross entropy, which we usually denote as like HP comma Q, is like the expectation of self information of some other distribution, right? So your variable is the same, but you're using some other distribution rather than this distribution, right? So yeah, we have HPQ is basically like it's negative expectation of natural log of Q. So basically like expectation of negative natural log of Q. This negative natural log of Q thing is called the self-information, and so you're just like finding its expectation using a different distribution. So it's basically like if using some other distribution you were to encode, right? You were to encode your elements, and then using so you use that encoding, but you don't actually get the distribution. You get some other distribution P, right? So using Q you encode it, but using P, so the data that you had was actually generated using P, right? And the average number of bits that you would need is basically this thing, right? Or at least the minimum bound on this thing is this thing. Yeah, and that's why so this is all related to information theory, and we shouldn't get too deep into this thing, but this has nice properties. Like this sort of stuff is used a lot in like in ML as well as in like physics stuff, so like statistics, mechanics, statistical mechanics and all that. Fine. What's the KL divergence again? Oh, it's just the cross entropy minus the self entropy. That's all it is. That's all you need to remember. Cross entropy of some other function with when you're having the distribution from this particular function, right? So basically what you're saying is, if you used Q to encode and now you're getting P, how bad is this going to be? And that's going to be the cross entropy minus the self, because this thing, this self entropy thing, it's going to be the maximum when, so basically self entropy is also kind of a cross entropy thing. It's going to be maximum when Q is equal to P, right? So we know, as a matter of fact, yeah, okay, shit, okay, something weird happened. Yeah, the cross entropy is bigger, and this thing is minimum, it seems. Okay, did I mess up something? It seems not. Okay. So usually the way it goes is, so entropy is okay. Yeah, I mean this is fine. This is fine. You would have the minimum number of bits if you did that. So this is a minimum amount anyway, right? So yeah. So if you were to encode using Q, right? How worse is your information content going to be, right? So like how much more bits will you require? Because so h of P is the minimum number of bits that you would require if you're going to like sample from the distribution P. And so Q is basically another distribution which you're going to encode using, right? So how much worse are you going to do? That's the KL divergence, right? So it's basically performance on P given you encoded Q, all right? And it's easy to see that this thing is actually positive. So this is this can be used as a distance measure, basically. All right. So this is all about distance functions. And let's go to objective functions. So distance functions are like useful for defining objective functions. So in our case, we're just going to deal with k-center and k-means. So you have the a few things. First, you have inertia. So I like to call it as inertia because it's like, although it's technically variance or something like that, but I like to call it as inertia. So basically you get the centers, right, for your points in the clusters, and then you think of like the clusters as being balls, sort of, right? Yeah. And so you take the inertia of each of these ball, and the center is the center of mass. You can think of it like that. At least for k-means, it literally is the center of mass. So you can think of it that, okay, so the inertia of these balls added up is like our objective function. We want to minimize that, in fact. And that's for k-means. For k-center, it's just the biggest radius that you want to minimize. So you want your balls to be very, very small, basically. So radius of cluster, that's for k-center, and inertia for k-means. So you can also use some other stuff. So you can use like, so first you define this thing called an intra-cluster distance. So intra means within, right? So within the cluster, what distance do you have? So like for one particular cluster, without referencing any other cluster, the value delta I is, well, it can be defined many different ways. First, you could just have diameter, like how thick is the cluster. That's going to give you a good measure of, you know, the intra-cluster distance, basically, like between any 2 points in the cluster, how far off would they be? And so this is like, okay, they're not going to be more than this far off. You could also have the average distance, which is like the expectation. So then you're saying, okay, they're probably going to be this far off. Or you could have average distance of points to the mean, right? And this is a bit weird. Like, I don't want to use this because this doesn't really say anything about the intra-cluster distance, but okay, sure, you can use that. So average distance of points to the mean, yeah. Cool. And then you have this thing called a Dunes index. So suppose you are given these intra-distance, so intra-cluster distances, right? And you have in fact another function which is called the inter-cluster distance. So given two clusters Ci, Cj, you can somehow define a distance measure. So this might be like the shortest linkage, or it's like the farthest away points. It's called complete linkage, or it could be like average. So it's like center to center sort of distance, or something like that. Yeah. You could have anything, right? So suppose this thing is also defined for us, depending on the context. Then the dunes, how you pronounce it, this index is given by the minimum of this inter-cluster distance upon the maximum of intra-cluster distance. So once again, the inter-cluster distance is something like how far off would 2 points from different clusters be, and this is how far off would 2 points be inside the cluster. And so this is maximum over I. So like from all the clusters, how big is any cluster? So the biggest cluster, you take that, and from these two, so like from all the clusters, you take two clusters which are the closest. So that upon the radius or whatever intra cluster distance you have, that's our Dunes index. And so this is basically giving you kind of a measure that how bad is this going to be, like, because if this distance, right, so if this minimum thing is going to be like really small, so like the two clusters are pretty close together and both the clusters are big, then that's a problem. So the smaller this index is, the worse off it is. The bigger it is, the easier it is to cluster everything together, right? So to cluster it correctly, that is. So higher clustering doesn't have an objective function, although it does use a distance measure. It has to use a distance measure, in fact. Yeah. So let's just get straight into the algorithms. First, k-center. So this is so the usual algorithm for k-center is called Voronoi partitioning. So the idea is pretty simple, that you just take away, so like, okay, so whatever kind of points you're going to assign as the cluster centers, for any random point that you choose from the data set, you'll just find the point which is the closest to it and you'll assign it to that cluster, right? And that's Voronoi partitioning. So this is for k-means, k-center, and pretty much for everything. But yeah. So k-center, the classic algorithm for this, is actually an approximation, because if you think about it, finding out which cluster set is going to give you the best thing, it's actually not that easy. It's in fact NP hard, and this is a complexity class. So but yeah, for like in a layman's term, what you can say is that it is how do I say this? I don't know, I'm just gonna say it's NP hard. Fine, this is good enough. Fine, so it's a hard problem basically, right? But you can actually have an approximation at least. So the algorithm for the 2 approximation, it goes like this. You initialize the clusters randomly. So first cluster you initialize randomly, and then so you want to have k clusters, right? So for I 2 to k, so for the second cluster, third cluster, so on, you choose the point which is the farthest away from the current set of clusters that you have. And when I say farthest away, it means that you get the minimum distance from the point to any cluster, and then that's the measure of farness of this point from the cluster set, right? And so you choose a point which has the highest value for this measure. So you have that point, that's your new cluster, that's a new center, and you add this cluster set, right? And then you reevaluate all your points distances using this thing, and that's what this thing is doing. Sure. Okay, so why is it a 2 approximation? Well, the proof is 2-part. First is when exactly one center is, so suppose Si star is the optimal set of clusters, then 2 things. First, you could have like all the cluster centers being in the correct clusters, right? So like 1 per cluster, where when I say cluster, I mean the optimal clusters, right? And these centers are the ones that you get from the algorithm, right? And then case 2 is at least 2 centers are in the same optimal cluster, and that's a problem that like leads to some bounds on how far 2 points can be, because of the way that the algorithm is. The case 1 is pretty easy to do. Case 2 requires some understanding of the algorithm, and I'm not going to go over the proof. I'll just link this in the description so that you can just read it on your own whenever you want to. But yeah, so this is k center, then you have k means. So the problem with k center is that it has a lot of scope for, I mean it does in fact do this all the time, that if you have an outlier, it will straight up declare that as a single cluster, which means that all your outliers must be given very high priority, and they'll all be called clusters. So like choosing the correct k value, it really depends on what kind of outliers you have. And so you don't want something like that to happen. You want to have a soft sort of thing that, okay, if you have an outlier, you'll ignore it pretty much, right? So for that reason alone, you have k means, which takes average square distance, right? So the objective function is this thing. This is what I call inertia, but yeah, this is the intra-cluster distance, and this is the full objective function. All right. So okay, this is called Alloyd's algorithm or Alloyd iteration. So it's a bit similar to the EM so like expectation maximization thing that you have in Gaussian models. Now these are all fancy words, frankly, but yeah, I eventually realized that this is kind of just an approximation to that, in fact. But yeah, so the point is that so what we're going to do is, first you'll randomly initialize your cluster centers, all the k ones, or all the k cluster centers will randomly initialize. Then you'll cluster Voronoi partitioning, and then once you have these clusters, you'll reassign these centroids, because these centroids, so I'm saying centroids rather than centers now, because these are going to be updated like that. You'll basically find the center of mass. Once you have the center of mass, assign that as the center rather than whatever it previously was. The reason is that is the one which will minimize the inertia of that particular cluster. So first step, it obviously minimizes the inertia, right, because it assigns it to the nearest. In the second step, it also minimizes the inertia, and then once again you'll do the same, that you'll reassign it. So since it's going to be always a minimum, it's always going to be better. So as you keep doing these 2 steps alternatively, like your objective function is only going to go down, it will never increase, which is a good thing. This is what we want, and eventually you'll reach the optimal or a optimal clustering, right? Now, how long will you have to wait for that to happen? That is a problem, because sometimes this is going to take like exponentially high time based on how bad your initialization is. So there are two pretty nice strategies to initialize. One is like you can choose randomly, right? You randomly initialize the points. Other is you can use some other algorithm, clustering algorithm before this. So you could use k-centers, but again that leads to the outliers being the centers, which is a problem. Or you could use some sort of combination, right? So you still keep it probabilistic, but you also use this fact that okay, you want the centers to have to like be far away or something like that. And so that's where k-means plus plus comes in. So it weighs the, so it basically is k-center except probabilistic. So you choose the first point randomly, and then as you want to choose a new point, right, you get all these so you get its distance from the current cluster set, you get it for all the points, and then you weigh it, right? So you weigh your, so it's like a lottery system where the probability of you choosing a particular point is proportional or sometimes squarely proportional to its distance from the cluster set, right? Yeah, so the probability is like, so you normalize it obviously, but yeah, so it's going to be like the distance from the cluster set to the power of q, where q is some number, right? So usually q equal to 2 is used, so that's like squared distances. And with this initialization, k-mean returns a, on average, time complexity is like log k. So yeah, I mean the worst case complexity is still going to be that, you know, you just, because it's, in the end this is a random choosing sort of thing, so you do not have a full, like you don't have full control, so you still have the worst case complexity being exponential, but at least the average time complexity is in fact okay, this is not actually a time complexity bound, it's, yeah, okay, this is a theta log k, this is a approximation bound, but yeah, once again the time complexity is also going to go down on an average, not in the worst case. And this initialization it also actually does not, so this is the not the worst case bound, this is a theta bound, and that's to say this is an average, on average you can expect it to be like log k more than what the optimal solution would be for k-means. So it gives you a theta log k bound, k-means plus plus initialization, and then from that you can do Lloyd's iteration again and again, and then there you go, that works. So if the clusters are nicely clusterable, this will just give you a order 1 approach, and here I'm saying order 1 and not theta 1, right? Yeah. Anyway, let's go to parallelizing k-means. So the time complexity for k-means is, so based on the number of iterations that you're going to run, it's going to be nk times capital N, where n is the number of iterations. And so this can be pretty costly. Can be pretty costly when your data is large. And so what happens when your data is large? What you have to do is you have to parallelize this thing. So you'll split your data randomly, right, completely randomly, into batches, and then you'll process these batches using k-means again, in fact. And then so you'll have like a bunch of like set of clusters, right? And so you'll weigh each cluster with the amount of points that it was like assigned, right? And then with this weighted sort of set of points, you'll basically like concatenate all of these sets with those weights, in fact. And then once again you'll run k-means on these centers, right? Not on the data points, but these centers, and you'll do it with weights, of course, because each center can have different amount of actual like points assigned to it. And so once again, this is an approximation. This is not even as good as what the normal Lloyd's and iteration thing would do, right? The reason this works is because when the data is so large, you are almost guaranteed that the data is going to work out, right? That's it's like the centers that you have, they'll be almost the same. So then it's just a point of refining and like creating an ensemble basically, and then resolving an ensemble to a single sort of thing. Yeah. So this gives us a order gamma beta approximation, where beta is the approximation factor for the subproblems and gamma is the one for final clustering, that is the clustering on the centers themselves. right? So the centers you get from the first step. Yeah. So most of the times what happens is you'll split the batches such that it's exactly k batches, and so yeah, so like since k means gives an order log k approximation, if you divide the problem such that both beta and gamma are order log k, this will give you order log square k approximation and so on. If you have like a 3 tier hierarchy, then it's going to be like a log cube k, etc. You get the point, right? So first we'll like split it into k batches, and then you'll run the you'll run this thing with k of these guys, and then once again you'll rerun it. So it's going to be log k, right? Hierarchical clustering. So this is sort of better, in fact, in terms of the output, but in terms of the time requirement, this is like really bad, and this also does not generalize and it cannot predict as much, and so this is still bad. But this is based on cuts, or you know, so there are two methods. First is like using the cuts method. So you have data, you iteratively split it into two like two different sections. So you cut the data, right, and then you keep doing this. That's one strategy that you can have, or you could build it from ground up. So that's what things like Kruskal's algorithms do, right? So this what we do is you think of each data point as a cluster, right? And then whenever you have two clusters which are very close, you join them, and that becomes a new cluster, right? So you replace those two by a single cluster, and you keep doing this. And so this joining sequence, it basically gives you some sort of dendrogram or a phylogram. So things like the UPGMA tree algorithm, or let's say Kruskal's algorithm for minimal spanning tree, these things work using this strategy, right? And so you can undo the last k steps, the k joins that you did in your dendrogram or whatever, and then you'll basically have the clusters. Yeah, because every time you undo a join, you're creating one more cluster, right? You're adding one more cluster to the set of clusters that you have. And so that works. And so there are like three different ways of having a distance between two clusters. One, you can use the smallest distance between two nodes, and that's called the single linkage clustering. You can have the farthest, that's called complete, and then you can have average distance. Now for one dimensions, you can actually have an exact algorithm for clustering, right? At least for k centers, you can easily have a optimal clustering just using dynamic programming. The problem with hierarchical clustering for this thing is that it doesn't work. Yeah, it doesn't work because it's very easy to fool it. Like if you have a bunch of points which are almost equally separated, except the distance between consecutive points is increasing just with a very small increment every single time, then yeah, and an algorithm, so like a hierarchical clustering, what it would do is, so a single linkage hierarchical clustering, it would just grow the tree from left to right, and that's bad because you are not clustering at all at that point. So it will just form a very tall tree. It's not nice. So you have to do some post processing to get it to the correct thing. Like you could have some sort of balancing operation, right? So you could have a left rotate or something like that in your tree that you have formed, and so that's going to solve this problem, but with a lot of wasted time and effort. So you don't want to be doing hierarchical clustering all the time. You only do it when it's useful. Now exact algorithm, that's just a dynamic programming thing. Yeah, and so the basic fact that this thing uses is that it's basically something like a cut. So basically every time that you want to, so like x1 to xn are the points that you're given. So suppose x1 to xi is what you want to cluster, and you're already clustered x1 to xi minus 1, but you'll, and all the previous ones, all the previous subsets. What you'll do is you'll figure out whether there's a cluster to the right if you form, then the left one gives you the left one and the right one's cost combined gives you a small value, right? And whichever of these right side cluster give you the smallest value, you'll just choose that. And yeah, this can be proved to be optimal. That's pretty much it. So this is an exact algorithm for k-means. Now this homework thing, yeah, it's a lot actually. I'm not going to go over this, but okay, let's just go over this. You know what? No, let it be, because these are just homeworks. And although they are very interesting, I do want to share this, but we don't have enough time. All right, let's go. Densest subgraph. So the density of a subgraph is defined like this. Actually, you know what? I'm just going to go to the recap straight away. I'm not going to do all of this. So expansion, conduction, Laplacian, sparsest cut, etc., etc. I'm just going to go to the recap. So the density of a subgraph is given by, so rho of s is defined like this thing. So it's basically the number of edges that you have. So edges connecting 2 points in the subgraph upon the cardinality of the nodes in subgraph. All right. The expansion is given by this thing. So it's E of s bar, where s bar is the remaining graph. So G minus s basically upon the minimum cardinality of either s or s bar. And then conductor is defined similarly, except it's the sum of degrees and not the cardinality. So whenever I say d of s, it means the summation of degrees of the points, and by degree I mean degree in the full graph. All right. So two very important identities are that ds plus dis bar is e, and ess plus ess bar is d of s. Yeah. So and then you have this identity. So the density of s being bigger than or equal to c by 2, that is the same thing as saying that this holds true. And this is an important thing because this gives you a way to solve the problem of finding the densest subgraph, and you use the minimum cut algorithm to do this thing. And we'll get to all that. Okay, actually, let's just get to it. So you can construct a different graph. So you're given a graph G, you construct a graph G dash with the same vertices, except you add a source and a finish like terminal sort of thing, nodes basically, such that there's a bijection between P of G, which is the power set of G, so like all the subsets, and the minimal cuts in G dash. All right, with this cost. So it's CS ds bar ESS bar. So this once again I'm saying cuts in G dash, and the cost is given by this thing, right? Yeah. Yeah. Cool. When you say the power set of G, so these S things are from P of G, right? So S is a subset of G, and that is directly connected to a minimal cut in G dash. Cool. So now finding whether there's a so now you want the minimum cut, right? So that this thing is minimized. And why you want to minimize this thing? Well, look at this identity, right? You want to minimize this because so that this inequality holds true, and if that holds true, then you have found a subset with density which is bigger than or equal to some c by 2, where c is something that you came up with. And so for any given c, you can actually find the minimum value of this thing. And once you have the minimum value, you can check whether or not this thing is less than or equal to 2e. And if that's true, you can say, okay, the density is at least as big as c by 2, right? And then you can do binary search on this c thing, because you know that the maximum density, whatever so you would know what the, actually you don't know the maximum density, that's a problem, isn't it? Well, I didn't think of that. But so the maximum density is when this whole graph thing would be a click. So G is a click. So you do have some finish point for it, so you can do it. It's just going to be like, yeah, it's going to be costly, but whatever. So you can actually do binary search to find the minimum C, where density of S is bigger than or equal to C by 2. So this is like one very exact sort of way to be doing this, like to find the densest subgraph or something like that. But you also have an approximation. So the Charikas greedy algorithm, it gives a 2 approximation for the densest subgraph. Yeah, so the algorithm goes like this: you start with a full graph and then you keep deleting nodes with the lowest degree. And so like you have graph G, you remove the node with the lowest degree, so now that's gone, disappeared, erased from existence. And so this subgraph is your new graph that you want to deal with, and you keep doing this. And yeah, so you just keep doing this, and then you get, so you have the densities at all different times, and so you just figure out, okay, at which iteration did I have the most dense subgraph, and then you'll once again rerun the algorithm till that point, and then you'll stop there and you'll return the subgraph that you had. Fine. Yeah, so that's this is all for density. There are also two other measures which are important. So it's called expansion and conductance. So expansion is given as, so it's called phi of G. So basically this is, yeah, just notation, phi of S. So the expansion for a subset S, that's going to be subgraph S. It's going to be like E of S bar upon minimum of S bar. Conductance, so I'm saying it's CG, although it should really just be phi. So it's phi sub C, in fact. That's how you write it. So the conductance is this thing. Once again, you don't write it as C, you write it as phi C. I don't know why I came up with this notation, but okay. Fine. So the conductance of a full graph is basically the minimum conductance of any subgraph inside of it. And so you want to reduce expansion and reduce conductance, but you want to increase the density. That's the main goal. It's a sparsest cut is any cut where your cut is basically like S bar, and the expansion or the conductance of S is low, right? Then that's the sparsest cut. And so how do you get the sparsest cut? Well, it's a hard problem. You can't just get the sparsest cut, but an approximation is using the Laplacian. So Laplacian is given as the adjacency matrix for a graph minus a diagonal for the degree of nodes, right? And usually you normalize this. So if it's like a regular sort of graph, then you would just divide this by the degree. So when you say regular graph, it basically means like all the nodes have the same degree. So you would divide it by that degree basically. In general, you just like you do some weird like change of basis sort of thing to do this thing, but whatever. The second eigenvalue is basically going to give us all sorts, and in fact like an eigenvector is going to give us the approximation. So I should write it as eigenvector, right? And this is really just worth reading. Like you should go and read all this on your own. But yeah, so this is the algorithm. Okay, this is actually the proof for it. This is like on the upper bound and all that. So there's a lot of algebra which I don't want to go into, but the algorithm goes like this: that you find the normalized Laplacian, you find the second eigenvector, it's also called the Fielder vector, and you sort the vertices by their absolute coordinate values in V2 from highest to lowest, and then you try the partitioning thing, right? So you'll want to put all the high valued ones on like one side and all the low value ones on the other side. Yeah. And this is guaranteed, so like you keep doing this in fact until you have completely partitioned it. Yeah, and this is guaranteed to give conductance phi c is order square root of phi dash c, where phi, so phi star c, where phi star c is the optimal thing. Now this is some measure which is less than 1, so square root of phi star c is actually more than phi star c. Just keep that in mind. So for non-regular graphs, you should use this Laplacian instead. Okay, anyway. And then you finally move to mixture. So there's a lot which is left. To mixture models. So here what you assume is that your distribution is coming from the mixture of multiple Gaussians with different means and standard deviations. And then the point is to, well, first have a likelihood measure, that how likely is a particular distribution of the means and variance values, and also the base, the prior probabilities, that's also variable. So like the probability of one model being favored over the other, right, which is also called phi sub I. So the point is that you want to optimize these parameters using the data, and you do this using maximum likelihood estimation, but it's hard. It's extremely hard to be doing this. So there are two things that you can do. One is an approximation. You can assume that the centers are very close to the points, and then that just makes it k-means, which is sad because we already did k-means and we know that we want to do something better. So that does not work. And the other thing is an iterative approach. And you, before you say gradient descent, just hear me out. That's not the only iterative approach, all right? So before you put this in an autograd system, because it looks doable, I can just put it in an autograd system. Gradient descent does not necessarily give you better results after every iteration, right? That's one of the basic truths, that it can overshoot. But we have in fact an algorithm which will never overshoot, and it's called expectation maximization. So it's basically k-means. Yeah. So what you do is you randomly initialize these parameters, then you cluster the data based on this thing. So when I say cluster, you actually find a probability distribution of it being in one particular Gaussian for every single data point, and so you find this, right? You find the probability of it being over here or here in some other cluster, whatever, and based on these probabilities you once again compute your parameter values. So you compute it like this thing. So Zik is basically the probability that you're going to be in a particular cluster, right? The ith point is going to be in a particular cluster, and then you can re-evaluate your parameters using this thing. You have phi sub k as this average, mu sub k as this average, and sigma sub k as this average, and yeah, that's how you do it. So that's mixture models. At least it's Gaussian mixture models. In general, mixture models need not have Gaussians as the elements of whose mixture you're going to have. You could have different parameters, but still the thing remains the same, that there's probably a better algorithm than just gradient descent. You should just find an algorithm and then do that. All right. But for Gaussian mixture models, there's obviously a better algorithm. So you should just do that and not think about gradient descent. Now, these next two sections are somewhat exploratory. So it's basically about high dimensional spaces, right? Because eventually what you want to do is get to spectral algorithm, which is some sort of low rank approximation, and then on top of that you're going to do k-center. So, and this is basically like going to be a very crude approximation for mixture models. But yeah, so it's something like k-means plus plus, right, where you're going to run something before the actual iterative approach, so that you get a better result. But yeah, so because you want it to be good, like, you have to study a bit of math first. So first is that vectors are always orthogonal in high dimensional spaces. So this is going to, so this whole thing is just so that you can have some sort of a feel for how close two Gaussians should be in a very high dimensional space, so that you can cluster them. And it turns out they can actually get pretty close. They can get very close, and you can still sensibly separate these two Gaussians. Yeah, and it turns out that okay, so first is that's actually some other thing. That was the other section. This section is all about like that if you're going to sample from a very high dimensional Gaussian distribution, then 2 points are almost bound to be orthogonal, which is weird. I mean, I don't know, but it is actually pretty weird. So the cosine similarity between two vectors that you're going to sample, that is of theta d power negative 1 by 2. So that's like theta 1 by square root of d. And so as d grows very high, this value was very low. So on average, your vectors are going to be orthogonal. That's what it's saying. Right, but yeah, we don't really care about this. We care about this one. So how far should clusters be? So some math from the last section we do care about, but yeah, so how far should the clusters be for them to be clusters, right? And so turns out if your variances are different, then they should be pretty far. They should be sigma 2 square minus sigma 1 square d square root of that far away. If your variances are different, if they are the same though, it's d power 1 by 4 times sigma. That's how far they should be. That's how far your centers should be. And then you have some stuff about chi distribution, which I really don't care about, because none of this was actually used. And then you have the spectral algorithm. So this relies on some very basic observations. First is that when you do a projection into a different space, like of densities, the densities, if they are Gaussian, they still stay Gaussian, right? So basically, even if you did some sort of low rank approximation of the data, it would still be Gaussian, still coming from a Gaussian distributions mixture, right? And so the idea is you do this low rank approximation using some SVD thing, right, some PCA thing, and in the lower rank density thing, you find out the means using and parameters using k-means pretty much. So you just run k-means or k-centers, and then you find out the centers in this low dimensional space for the data, right? And it also tells you some other things. It tells you phi sub I, because you also have like the data points being assigned to the clusters. So you know like how probable is it in general that a point would be assigned to a particular cluster, right? You also have like the variance, because obviously you can compute the variance once you have the data itself, right? Yeah, and so using all of that, you project back to the higher dimensional space somehow. Now don't ask me how do you do that, or you just stay in this low dimensional space, I don't care. But after that, you basically run a proper EM algorithm, you do the iterations, and yeah, so that is basically your model. Your model just turns out to be a lower dimensional projection, and then using your GMM model to do classification. That's it. That's what your model becomes. And that's a spectral algorithm. We say it's spectral because it uses SVD. Yeah. Okay, and now we are going to big data handling. So first, so this is going to be about some very basic objectives, and our two main objectives is one, the so first one is just like linear counting, which is basically like the how do I even say this thing? Yeah, so basically it's like sampling. So you're given a data stream and you want to sample some fixed number of values from that data stream, right? Like you have a stream of running water and you want to have a jug full of water from that. It's basically that. So how do you ensure that you get a good sample which represents the distribution? And so you can't just like, since you don't have all the data available at every given moment, you can't just like, you know, generate random numbers and say, okay, at this index I'm going to take this value, at this I'm not going to take this value, etc., etc., which is, by the way, a correct thing to do. I mean, this is okay, but if you just don't have that kind of memory capacity in your computer, and I don't know, it's some sort of signal, continuous signal that you're generating, you would probably want to use some other algorithm to do this, and the go-to algorithm is something known as the reservoir algorithm, right? So if you know your size, right, if you know the size, then you can just simply generate indices, and then whenever you have the index, you just take it, right? But obviously you don't know your size, you don't know how many items you're going to observe, and so that's where this R algorithm comes in, the reservoir algorithm. And this is pretty easy. It's on Wikipedia, by the way, and its working is easy, its proof is easy. All you have to do is first k samples. So you want to get k samples from the stream of n samples, in fact, and it's not known to you, but yeah. So all you have to do is, well, the first k observations that you see, you'll just put that in your final answer, right, in the reservoir basically. And whenever you'll see a new sample, you'll pick one index randomly from 1 to I. So for the ith sample, from 1 to I. And if this thing is less than k, you can put it in the reservoir. Yeah, otherwise you can't put it because the reservoir is like only k long, and so you discard it and you move on. And that's it. That's the whole algorithm. There's nothing complicated about this. And it turns out this is a good algorithm. This basically gives every data point the equal chance to be in the reservoir at the end of your whatever process you're doing, right? So as the stream is done and you're going away or whatever, every element, every observation that you saw so far has an equal probability of being in the reservoir, right? Yeah. So that's sampling. Next, you want to do something known as frequency. So it's either like you want to have you want to create distributions. That's one thing you could be having, or you just want to have the different type of unique elements that you'll observe. So it's called distinct counting. This is linear counting, this is distinct counting. So one obvious way to do is hashing. You just have a hash map, and then in that you can store the frequency. And this is what we usually do. But this gets problematic. And the reason for this being problematic is because when you have a hash map, you also have this big, huge table of linked lists where you're actually storing the elements. And sometimes these elements can be massive. And that's not good, because it's a lot of memory that you would need to do that. And so instead of that, if you're going to just use it for some statistical thing, well, it's okay to miss it's okay to have a wrong output of belongingness in the set. Sometimes it's okay. So in that sort of scenario, you shouldn't use a hash map, because a hash map is for very precise sort of analysis. Here you're not dealing with precise analysis, you want to deal with lots of data. So the way to solve this is using something known as Bloom filters. So hashing is a bad idea. I mean, okay, so hash maps are a bad idea. Hashing is actually a different thing. Hashing is just hash functions. So this stuff is about different sorts of hashing. So you can have uniform hash family, universal hash family, near universal hash family. We don't care about any of that. We care about the algorithm. And so we are going to go to a Bloom filter to do distinct counting. So the idea is, every time you see an observation, you pass it through k hash functions, and then these hash functions will give you indices. So you only have a very small array of size m, and so after you get these indices, for each of these indices you will set the bit array's value to be 1 at that index. And so when you are going to query, right, so is this particular element inside this inside this set that we just saw, the set of all elements that we just saw? If it's 1, right, if it's 1 at all the places, then yeah, sure, it is. Otherwise it's not. Though that's your algorithm, that's what you will return at the query point. This is an approximation. This is not necessarily correct, because it could be that, okay, so first, if it's not there, it's like all of these entries are not 1, then obviously it's not there. So you can never have a false positive, but you can have a false negative, right? You can say that, you can never have a false negative, but you can have a false positive. That is, you could falsely predict that it is there, although it isn't there, and the bits are only there because of some other elements being hashed, and like those indices being set. And so what's the probability of this false positive rate? Well, it's this thing. It's 1 minus e power negative nk by m up to the power of k. Yeah, approximately, by the way. Looks disgusting because it is disgusting. But what you end up doing is that you want to minimize this false positive rate, and you do that by obviously taking a derivative. As you take a derivative, you solve this whole thing, and turns out that the value of k for a given m and n, where this is optimal, right? If you already know the n, and n is too big, basically, and you also are kind of limited by your hardware, so your m is also fixed, then the best value for your k is going to be m by n natural log of 2, and you get all of you have to do all this analysis to get to this point. And so when you set k to be that thing, so k is once again number of hash functions that you're going to use, then the optimum false positive rate is going to be 2 power negative m by natural log of 2, right? So basically to get a positive rate, positive false positive rate of delta you or less, in fact, you need at least this much of space. It's negative n natural log of delta upon natural log of 2 squared. So basically order natural log 1 by delta amount of space. So for example, for a 1% error rate, you would require 9.6 n amount of bits, all right? So that's basically like almost 10 bits per element. So for a hash map, you would require like lots of bit per element, because an element is a lot of bits itself, right? Once again, remember, you have to store the elements in the linked list. Important, right? But in this case, you just require 10 for each element. Well, for each unique element is what I should say, right? So now you might think this order n space thing is a bit impractical, but hey, hash maps are even more impractical. So this is actually much better, in fact. Now this is for belonging and all that, right? That whether a particular element belongs in this set of values that we just saw. What if you also want the frequency, that how many times did you see this element? Well, then you use something known as a counting Bloom filter. So instead of just incrementing, so just having a bit array, you have an array of counters. And so this is more or less like you have to do this at the hardware level or something for this to be very optimal and time efficient and real time and all that. But yeah, so you should have an array of counters, usually a 4-bit counter, because if it's 4-bit counter, it's like 2 power 4 is equal to 16 is the amount of data that it can store, right? So the frequency could go up to 16 basically. Yeah, and so like if you're dealing with something, I don't know, you have a signal and then you sample the signal using some analog to digital converter, and yeah, so something like that, then it's probably a good idea to be using a counting Bloom filter with like 4-bit counters. Of course, sometimes you might need more, like much more, but then there are algorithms which you can use to have arrangements where you still have less space requirements, but you can actually count much more. So yeah, that's counting Bloom filter for obvious reasons. So counting. So every time, once again, you get an element, you hash, and all of the k different indices that you'll get, they may not be different, but k indices that you'll get will increment the value at those values, at those indices. Yeah, that's hashing. So that's Bloom filter, and then you have linear counting. So there are Bloom filter is not the only way to be doing these sort of things, right? There are other algorithms as well. One algorithm is this thing. So basically, you maintain a bit array and you have a single hash function, and so when you observe an element, you set that hash functions, so the bit array at the value of the hash function as 1. And so this is what this is counting, is not the frequency of the elements or whether or not the element is going to be there. So it's not that you actually have queries after this thing. This is just counting the number of distinct elements. Yeah, so this is linear counting. This is number of distinct elements. Okay, so I said that linear counting, distinct counting are different things. It's not. Linear counting is a part of distinct element counting. I think the thing that we're doing previously, that was sampling, which is a different thing. Sorry for that. Yeah. So once again, the traditional hash table approach, not so good. Also, you can't use a Bloom filter because even that is like expensive. Yeah. So what you end up doing is just having like one hash function. One hash function, one bit array, observe an element, set b of h sub h of x equal to 1, and after everything's done, you'll count the number of unset bits and you'll return this number, negative m natural log of z sum m upon m, as the number of distinct elements. And this is weird, obviously, like what is this expression, where did this even come from? And it came from expectation. So basically, like given S is the number of distinct elements, the expected value of unsent bits is basically m e power negative s prime, and then you reverse this thing, so to get S as a function of Z sum m. Yeah, and yeah, that's an algorithm. It does not give you any guarantees or whatever, but it is an algorithm. And then there's this thing. It's called the FM sketch, and it's once again another algorithm to do the same sort of thing, but this is much more popular and much more in use. And yeah, so this is the algorithm. So you define the zeros of a number as the number of, so this is not and, this is as the number of trailing zeros at the right side of the binary representation of the number. So basically the index of 2 in a particular number, with a special case that the index of 2 at 0 is 0. I don't know why I set it to be that. You can, so if it's like going to be L bit numbers, then you might as well set it to be L, but L is congruent to 0 mod L, so it's like fine, it doesn't really matter. Now you set a hash function which takes in this whole universe of different entities and assigns a binary binary representations of a number in 0 till 2 power L minus 1, and it does this randomly. All right. Oh, sorry. You choose this hash function randomly. Yeah. It doesn't do anything randomly. The assignment is fixed. It's a function in the end. Fine. Now, here's where the algorithm becomes. You set a variable z to be 0. For every x in the stream, you compute the zeros of h of x, where h of x is the value of the hash function of this element, right? So the zeros of hash, you calculate that, and if this number turns out to be bigger than z, you update z, and then you return z plus 0.5 raised to the power of 2. Sorry, 2 raised to the power of z plus 0.5 as the number of distinct elements. Now the reasoning for all of this is pretty I don't know, boring, because there's a lot of stuff that you have to prove. Basically, you have to prove these two bounds or something, and then after doing all of this, what it turns out, this isn't even all that good actually, because the probability that your value that you are returning, right, the 2 power z plus 0.5 thing, this s hat is basically this thing, that it falls like in the range s by 4 to 4s, where s is the actual number of distinct elements, as only bigger than or equal to 0.3. That's what you can prove so far. So this is pathetic, basically. It isn't good. That's what I'm saying. But you can make it much better. You can make it better by having medians of multiple estimates. So you run a bunch of these things in parallel, and then once all of that is done, you just take the median of the answers from all of these, and that is massively better, right? How better? It's exponentially better. Like the more of these different parallel sort of algorithms that you will run, the better it will be, right? So basically it's omega e power negative k, where k is the number of estimates that you're going to have. Okay, that's cool. But there's yet another improvement that you can make, and that is medians of means. And this is a complicated thing at this point. So to get the final estimate in the interval s to 1 minus epsilon to s times 1 plus epsilon, with the probability 1 minus delta, where delta is the error rate, you should first run the algorithm minus natural log of delta upon epsilon square times. But what you'll want to, so you just run all of these in parallel. Now once you get the results from each of these runs, you'll divide the results into groups. How many groups? Negative natural log of delta groups, and each group will be of size 1 upon epsilon square. Yeah, and you just do that. So like you get the mean from each group, and then you take the median for all of that. So that's medians of means. Cool. The proof, if you really want to see it, it's long. It's part 1, then you have a part 2, and yeah. So I bet it's better to just read all of this. But yeah, this basically goes on Markov's inequality and the Chernoff inequality, right? That's what you use to do the proof. Yeah, and so this is it. This is all that I've written so far for data science. So I'll see you guys in the next video. Bye.